Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'd like to welcome all of you here. Of course, we are here to celebrate Butler. He is one of the all-time greats of computer science. Fittingly, many of the other greats of computer science are here to celebrate with us. In fact, Madhu and Barbara and Chuck, who did a phenomenal job putting this together, told me that they have never seen people get back to them so fast. I mean, when they asked people to speak, it was, 5 minutes, and almost everybody had said yes. For those of you who've known Butler for years, for many of you who are speaking, you don't need me to tell you what he's done, but there are a few youngins out there who may not know all the things that Butler has done. So let me tell you a few highlights. His Turing Award citation in 1992 is for contributions to the development of distributed personal computing environments and the technology for their implementation. Workstations, networks, operating systems, programming systems, displays, security, and document publishing. Now, that is a long list. That's a really, even for a Turing Award, that's a really long list. So Butler really touched everything. Also in 2004, with Alan Kay, who is here, and Chuck, and Bob Taylor, he won the Charles Stark Draper Award for the vision, conception, and development of the first practical networked personal computers. And of course, this is what Butler is really known for. He will be forever associated with the first practical networked computer, which is the Alto. Also for his Wildflower blueprint for subsequent computers, but also for being an integral part of the team at Park that did so much. It's just incredible. And that, every lab since then, has said, okay, we want to do what Park did. And no lab has quite done what Park did, but what they did there was, the laser printer design, two-phase commitment protocols, Bravo, which is the first WYSIWYG text formatting program, the Ethernet, and programming languages such as Euclid. So this is really, it's just an amazing list. Hopefully, we will be hearing a little bit about some of that time and some of those really great achievements. And of course, Butler has since then continued to help all of us to design systems that will help move the field forward. But there are other things that you may not know about Butler. He doesn't just advise on technology and on computing. Well, Butler advises on everything, of course, but he advises on organizations. So Christian and I were incredibly blessed to have Butler give us lots of advice as we set up this lab. He was always telling us what Bob Taylor would have done. And and I think we took a few of those suggestions, and so this lab has this little piece that ties us back to Bob Taylor. But his sense of style goes way beyond technology. So interestingly, 2 weeks ago in the Financial Times, there was an article called "Can We Equate Computing with Art?" And that article extensively cited an obscure an obscure editorial by Butler from 1972 in Software Practice and Experience, in which he talks about programming and looks at it on the spectrum of creative endeavors from aircraft design to poetry. And, you know, that gives you a little indication of just how Butler thinks. I mean, he thinks about this spectrum of creative design. So those of us who have gotten to know him well know that he has an incredible sense of style. That style goes into many different areas. He and Lois have a phenomenal art collection. And they really, and not just one certain kind of art, but a real appreciation of many kinds of art. Music, they love music, and they're very involved with music. They have a great knowledge of music. They also have, I think, the most spectacular garden in all of Cambridge, with phenomenal roses and peonies. And I especially like this because every week Butler brings in these unbelievable flowers. He can tell you the pedigree, you know, of each flower. And he brings them for himself and for Irene and me. So it's really, really nice. Christian said he wanted some, and Butler said he wouldn't bring flowers to a guy. So so it's funny, when we first moved here, you know, people were warning me. They said, "Oh, you're gonna be dealing with Butler, and he's kind of uncompromising." And you know, for people who know me, I think uncompromising is a feature, not a bug. So we have lots of uncompromising people, and we really have fun together, not compromising with each other. It's really fun, actually, when we're uncompromising in the same way, though, and kind of everybody else is on the other side, because if Butler's on my side, I know I'm going to win. So he has brought his uncompromising standards and his style, his graciousness, and his unbelievable generosity to this lab and to the whole field. We're really, really lucky to have him in our lives. Okay, now we are going to have an amazing day of talks. In the interest of time, we are not going to tell you the backgrounds of each of our speakers, which are phenomenal, but you know, they only have 20 minutes to speak, and it would take, you know, a large part of that, because most of them are, you know, the father or the mother of something grand. So let me assure you, even though we are not going to tell you their backgrounds, they're incredible. If you don't happen to know, just Bing them. Okay, so okay, our first speaker, is it time for our first speaker, or should we wait just a few? What? You're happy to start. Let's wait 5 minutes for all the people who didn't want to hear me but want to hear Chuck. Okay, so we're actually, for a snowy day, we are doing pretty well. Okay. You go for it, Chuck.
Yeah, that article actually, the Software Practice and Experience article, actually predicted the existence of Microsoft. In the sense that until that time, virtually all software had been supplied by hardware manufacturers. And the idea that there would be an independent software business and that hundreds of people would try to program and that hundreds of people would try to sell those programs appeared in that paper.
Right, and actually the App Store even.
About Microsoft specifically. But yeah, I definitely intended the idea that there'd be lots and lots of people independent of hardware manufacturers would be doing programming. Not just Microsoft, but you know, all kinds of independent people Now we have 1 million iPhone apps written by, I think, several 100,000 different developers.
Yeah, as I read it, I was thinking, wow, this is the App Store. So why didn't Microsoft listen more carefully to Butler? But of course, as Butler will tell you, at many points, we should have listened more carefully to Butler. Okay, so I am going to be a really really severe timekeeper here, and I hope that our other program chairs will be really severe timekeepers, so the speakers are forewarned, okay? So our first speaker is, probably Butler's closest colleague ever, Chuck Thacker, and he is going to talk about the Alto architecture. And he's from MSR.
Thank you all. I'm somewhat surprised to see the large number of people, many of whom I don't even know. But today I'd like to tell you about a machine that we built at Xerox PARC because it has some interesting properties, some of which are still relevant today. This was not the first computer that Butler and I had worked on together. We started out in 1967, initially at the Genie project at Berkeley and doing the SDS 940, and later at the Berkeley Computer Corporation, and then at Xerox PARC. So this was actually our fourth machine, which is good because we were, by that time, seasoned. So in 1972, Butler wrote a memo, there's the first paragraph of it, proposing that the laboratory build some number of copies of a funny-looking machine that I had tried to design that had some new properties, and he says it might be interact with every CSL project. And sure enough, it did. So before telling you about this, I'll have to tell you a little about how systems research at PARC worked. The main tenet of the thing was that we had to build and use real systems in order to understand their value. Most people don't do that these days. And as a result of that, we missed some things. We didn't need spreadsheets, so we didn't invent them, although we came very, very close. The highest priority in the laboratory was hiring the best people. That was number one. And the sources of people were from all over the place. The BCC group, Utah, Stanford, SRI, CMU, MIT, will drag in people from anywhere as long as they were the best. And good leadership helps in this quest. And Bob Taylor provided that because he had actually paid for the educations of many of the people in the laboratory, and he knew everybody. So he had come to us from ARPA and ran the lab for many years, and I'll say more about that in my remarks this evening. So the organization of PARC was actually into 5 laboratories. It was set up more or less like an academic environment. The computer science lab was under Bob and Jerry Elkind. The system sciences lab was initially Bill Gunning and eventually Bert Sutherland. Alan's learning research group was in this area. The general sciences lab was mostly physicists, and that was Jerry Lukowski. The physicists were a little bit funny because they were sort of a fish out of water, and Taylor didn't like them all that much. I thought they were really great because whenever the Xerox Corporation, which after all paid our bills, had troubles, they could turn to the physicists and generally get some pretty wise answers. So I think they paid their way. But Bob and I have disagreed about this for 30 years, so we're just going to have to continue to disagree. The optical science, and I started out to be a physicist, by the way, so I have a soft spot in my head for physicists. I know. John Urbach ran the optical sciences lab, and this is funny. Why optical science, for crying out loud? Well, one of the big components of xerography was, in fact, optics. And we had a very energetic optical engineer named Gary Starkweather who did the first laser printing engine. And so he was in that lab. And later we had an integrated circuits lab, which was, to some extent, thought up by me, and it was the worst idea I've ever had, because we spent like $15 million, and this was maybe 250 today, building this thing which never made anything. And the reason is I didn't know that in order to run a semiconductor fab, you had to actually keep it busy at all times. And you couldn't just build experimental things and then go off and build some other experiment. You had to run product through it. And that didn't work, so this was a complete waste of money. The timeline is here. PARC was founded in 1970. It was originally supposed to be on the East Coast because that would make it closer to the mothership, but finally they decided that it was having two good universities close by was more important, and so it was set up at Palo Alto, with Berkeley and Stanford being the universities. The labs grew to critical mass over the next 2 years with a lot of hiring, and in the midst of that, we built the MAX time-sharing system. Now, we had all had quite a bit of familiarity with time-sharing. We understood it very well, and we wanted a PDP-10 because the ARPA community used PDP-10s, but Xerox had just bought a large computer company called Scientific Data Systems, and we were a little bit nervous that they wouldn't like us buying a PDP-10, so we built one. Well, I've mellowed in my old age, Alan.
Actually, it was great. They asked us for a financial justification of this decision. So we wrote down what it would cost to do this building and so forth. Then we wrote down what it would cost to buy the high-end SDS machine. That was not too significant. But then we wrote down what it would cost to write the programs to make it useful for research. And of course, we got to make those numbers up.
So there were, when we finished Max, we finally took a little break and finally started listening to Bob Taylor. He'd been telling us what to do for a long time, but we didn't understand it. And I'll get to that, I think, on the next slide. So we built the Alto, and SSL built Polos, the PARC online office system, which was based on a pile of many computers strapped together with somewhat better displays, but they didn't have quite the same properties as the Alto displays, so they never made it. In 1974, the Ethernet Alto research character generator and slot laser printer first came to light, and a lot of other printers followed. And of course, Xerox never made any money on our part of the game, but they sure made a lot of money on printers. So PARC actually paid for itself. Of course, software is always the important part of a thing like this, and a lot of applications and other projects grew out of the Alto, just as Butler predicted. In 1977 through 1983, attempts were made to make money at it, and most of those were unsuccessful. Charles participated in one of those. And finally, in 1983, again, generously, Alan, CSL dissolved. So here was one of those computers. This is the father of the Alto. This is the Max computer. The name is both an acronym and a pun. Multiple access Xerox computer. It was actually named at a party after a little bit of beer had been drunk, after Max Palevsky, who was the president of Scientific Data Systems. This machine was actually the end of an era because it was completely superseded by scientific workstations. The memory cabinets, which I designed, are the four on the right. Butler designed the processor. He decided to dabble in hardware a little bit, and I think he decided after doing this and spending the time to debug it and get it working, that he would go back to software. It was actually more tractable. But you never actually built it yourself, Butler, or debugged it.
I never built it myself, period. I debugged a lot of the Dorado.
You didn't build that. You didn't build
that. I had this great deal with Chuck. I designed the processor. I had learned about Maxwell's equations when I studied physics, and I understood about Boolean logic. I didn't understand much about the space in between, and I didn't want to. So my deal with Chuck was I would design this processor, and if I ever saw anything that wasn't 0 or +5 on the scope, I would yell for help. That only happened twice.
But in any case, for a while, that was actually...
You know what it was like at Park, this is it.
For a brief period of time, that memory system was the largest semiconductor memory on the planet at 3.2 megabytes. So where did we get all the ideas? Well, there's a whole list of things that have been cited over the years. Vannevar Bush's paper on the MIMEX in 1945. Lick and Taylor wrote a paper that was the thing that he was trying to tell us, which is the computer as a communications device. Doug Engelbart had demoed the mouse, which we quite liked. We also initially quite liked the 5-finger keyset until we discovered that the only person on the planet who could run it effectively was Doug himself. And so we had to leave those out. And of course, there was Alan's Dynabook and ideas that had been fermenting in the back of the minds of the VCC mob. And so those all came together to make that. So that's an Alto. Looks pretty modern, doesn't it? I mean, it's a little bit bigger. It's still the same color as the PC under your desk. It has a display, and you can see the mouse there, and the keyboard. And it's a little bit curious because the aspect ratio of the display is portrait, not landscape. Why was that? It looks much more like a document, right? It's a piece of paper. And that's the way we thought about it, because you could do anything. The Alto really only had 2 good ideas in it, and I'll tell you what they were one at a time. The first one was the bitmap display. The idea that you could represent the picture on the screen as a pile of bits in memory, and that any program could manipulate those bits and produce a picture. There was another one, but I'll tell you about that later. Okay, that's a 2.5 megabyte disk on the left with the Alto processor.
Removable disk.
Okay, so what's removable? It had to be removable, of course. Because initially we didn't have a network. So we didn't have distributed personal computing yet. We just had the computing part. Why is it interesting today? Well, because it was a personal computer. That was a new thing in the world. As Jim Morris said, it was very interesting about the Alto because the nicest thing property it had was that it didn't run faster at night. It was a platform, so a lot of software was written for it, a lot of which you use today. Hardware based on it, and it was used for research in universities. We gave some of them away with Dover printers, and it was not a commercial success, although as I said earlier, laser printing was. The technologies, well, wimpy memory from Intel. We used the boards from Macs, and what we didn't know was that they didn't really work. We found that out a bit later. I can tell you about that story offline. Boards were wire wrap commercial technology, medium scale TTL integrated circuits. CMOS hadn't been invented. It was reasonable in those days for a research group of our size to build their own computers and use them. You can't do that anymore. There's what 96,000 bits looked like in 1972. That's about this big. Today, you can't even see 96,000 bits. Here's the primary engineering team. That's Ed McWright on the right. Ed did the disk subsystem for the Alto and also a few other things like invent the B tree. There's Alan in the middle. There's a somewhat younger me, and Larry Clark, who was our technician. I think this was about the first time the Alto actually worked. And of course, the first animated bitmap graphics in the world was this picture, the Cookie Monster eating a cookie. And of course, we captured that for posterity here. But for the technical in the audience, that gives you an idea of the boards that we used to build the system. So here are some comparisons. It cost about $105,000 today. We definitely did something weird at Park. We spent money to simulate the future. A lot of people today want the future, but they don't want to spend the money. Uh, the CPU clock rate was 2,000 times slower than my machine at home, 48,000 times less memory, 17 times slower in latency. Only 150x in terms of pixels, but where my eyes were running out. So that's okay. Network is 300 times faster. And the capacity of the disk is 280,000 times. People think Moore was a real wonderful guy because he gave us 1.8x per year. The disk guys have done much better. And the people who've actually done even better than that are the people who make fiber optics. So here's the processor. You're not supposed to look too closely at this. There will be no quiz. The point of this is that it was pretty simple. You could put the entire block diagram at a fair level of detail for the entire machine on one page. So the stuff down at the bottom was the arithmetic unit in the memory. And you can see the second good idea in the Alto here. The idea was that the I/O devices connected directly to the main data highway inside the processor. That's this processor bus down at the bottom. And as a result, they could make use of the Alto's microcode rather than using specialized hardware. And this was incredible because it reduced the cost enormously. And you could customize and do things in that microcode that you couldn't otherwise easily do in hardware. So it was easy to use in that respect. So the emulated machine looked like a Data General Nova. Most of you have never seen a Nova, but it was pretty simple, RISC-like machine in 1960, roughly 8. Competitor to the PDP-11 or PP-8, and they lost. So you could hook I/O devices up to the Alto in a number of different ways. You could run them with assembly programs or BCPL programs. You could run as a part of a timed task in microcode. You could connect either to the low bandwidth parallel port or the memory bus, or to the direct main highway, as I described in the last slide. And we hooked up a lot of different kinds of devices. A lot of other laser printers. The initial laser printer used a specialized character generator to do its raster scanning, which could print fonts and limited graphics, but we didn't like that. So Bob Sproul built a thing called the Dover, which was a full bitmap. And then we did color versions, and we did something based on the Xerox 9700, or that was the Xerox 9700. A lot of other computers. The Dorado was the biggest and the fastest, but there were some others. There was the Dolphin, which was an attempt to build a faster Alto, but it never really took off because it was superseded by a few of these other three, Wildflower, Dandelion, and Dicentra, which came out of a design that Butler did primarily for the business group that tried to commercialize it. The Dragon was the last machine we worked on. It was actually a multiprocessor, and it was actually going to use LSI chips. But we disbanded before that. Lots of gadgets. We built Alan an electric organ, for instance, which he quite liked. Lots of software. The original Alto OS, a single user display based on a thing that had been done in England by Stoyan Strachey. The pilot system done for the System Development Division, and finally the Cedar operating system, which was primarily for the Dorado, for the Dragon. Software, lots of languages. The only one that didn't really work was Lisp. We didn't have enough memory. A lot of applications. Bravo, you'll hear more about that today. That morphed into Microsoft Word. Laurel was an almost recognizable email system, recognizable today. A lot of drawing applications. We like that bitmap display. A lot of servers. For mail, we had Grapevine, which was probably the first true distributed system. Oh dear. Miscellaneous software. Yeah, people think that Robert Morris launched the first worm. The first worm was actually done by a guy named John Schock at Park, and he managed to bring every Alto in the building down with a worm. Lots of communications software, which became what we see today in the internet. A lot of exploitation attempts, never really worked. The whole population was about 1,500. Successors, lots of extinct scientific workstations. The Alto was the predecessor of those, and they lasted for about a decade. And then finally, when Intel got its act in gear and started building high-volume processors, we got things like the PC. PostScript became from us. And, of course, Microsoft Windows and Word. And here's the final group from Xerox. So it was a good run. We had a decade there, and I'll say a little bit more about some things that happened after that this evening. So thank you very much. And I see I have 6 seconds. So since we had to race, we have 0 seconds. So we have exactly 5 minutes for questions. Okay, there's a test here. Who in this room can identify Mike Schroeder in this picture? Okay. I gave this test at the Silicon Valley lab of Microsoft, and nobody that I gave it to could find him out. Now, Andrew Birrell is a little hard to find, too. Roy is actually... Yeah, that's right. Butler had decamped to Philadelphia by this time, so in fact, he's not in this picture. No, he was one of the first telecommuters when we did CERC. Other questions?
Guy with the coffee cup?
Next to the guy with a coffee cup. That's Schroeder.
Yes.
Really?
Yeah.
Why are you surprised? Chuck pointed out Jim Hornick.
Yes, the guy sitting in the front row to the right of Bob Taylor, who looks like Jehovah, that's Jim Hornick.
Abe Lincoln.
You should point to yourself.
Say what?
You should point to yourself as well.
Oh, I'm in the back row. I note that I am a little grayer than I am in some earlier pictures. The reason for that has nothing to do with Park. It had to do with the fact that my daughter just became a teenager. Yeah.
Why do you think the commercialization didn't succeed?
Because Xerox wasn't a computer company. They had no idea what they had. And they were doing pretty well in the copier business. And when you have this big fat cash cow that you can just milk, and you have these upstarts coming and saying that they know what you ought to be doing in the future, you ignore them. And they were right. I mean, happens all the time.
You said laser printers were in.
Well, they understood laser printers.
Incredibly difficult even to make the computer printing, to push it through.
Yeah, IBM got there first.
Story about the failure of the office systems is actually a little bit more interesting because they had a very good engineering team, and this engineering team had a vision of what it was that they wanted to build. And they built it, much to my astonishment. I didn't think they'd be able to do it. And they shipped the Star system in 1981. And it was better than anything you could buy from anybody else for at least a decade, maybe longer.
One problem.
The problem was that it was too expensive.
Yeah.
And the secondary problem was that it was very hard to add anything to it. And the irony of this is that back at Park, there were people like Chuck and me who were saying to these guys, this is too ambitious, it's going to cost too much, you should build something much more like the Alto. But they had a vision, and they didn't do that. The fundamental problem they had, I think, was they had very good engineering, but the Xerox Corporation was not able to figure out how to provide them with marketing. And as a result, they were just like babes in the woods when it came to selling this stuff. It was very sad.
It was interesting. It was about the same price as dedicated word processors, which were much easier to sell.
Right. Oh, by the way, Apple made exactly the same mistake. They built the Lisa, and it had exactly the same properties as the Star system.
Yeah.
And it failed for exactly the same reason.
Yeah.
But they had a second go around with the Mac.
Yeah, it wasn't as good.
Which Alan described as the first computer good enough to criticize.
Over the back there.
Thank you. Could you say a bit more about the shift to seeing this device as a communication device? Like, I would love to hear what it was you
Well,
saw.
Taylor had written this paper, and he said that what computers are is not to do computations, but to enable people-to-people communication. And of course, we see that today in spades with social networks. So it was a prescient vision, and we just didn't understand him. As soon as we got into gear and we built things like the Laurel mail system, it took off like gangbusters. I mean, mail was all over Xerox, sometimes to Andrew's disgust when he would get calls late at night about a server that he'd never heard of failing. Okay, we have 19 seconds. And so I will take this opportunity to introduce the next, or are you doing the introduction?
Go for it.
Charles and I first met at Berkeley Computer, although he had worked together with Butler at the University of California. He was in the other computer science department. I was really shocked by Charles one day because in those days, the software engineers had the machine at night and the hardware people had it during the day. And we sometimes had dinner together when they would come in. And Charles came in one time with a large pile of camera equipment driving a yellow Jaguar XKE. And I said, Charles, what have you done? And he said, I bought it. I said, how? And he said, I bought a credit card. And I said, Charles, you got to be very careful about credit in America. It's a trap. You'll get in debt and you'll never get out. And he says, oh, no, this is not a problem. I'm going to be rich. I know I can deal with this. So here's Charles.
Thank you, Chuck. Yeah, I believed in the future. That's what it was. I always thought that I wish that if there would be a time machine, that somebody would send me money into the past. You know, my future self would, because actually I was very poor at the time, and no money came, and but then I realized that drawing on credit, if somebody gives you credit, is a way of time machine and sending money back into the past. So I looked at it exactly that way. So I'd like to put some parentheses around Chuck's talk and describe the years before and maybe after the Alto, and how my life intersected with Butler and the wonderful memories that we had together. It all started in Berkeley. That was called Berkeley also. I never liked that term, but now looking back, I think it was probably deserved. I arrived, 1967 was the Summer of Love, as you remember. You might remember. I arrived in the Autumn of Love. And as barely speaking English, this is a wonderful sunset looking from Berkeley Hills, original picture. And this is, of course, the student union, people I'm mulling around and singing and what have you. But every once in a while, a riot breaks out and there is tear gas on the way to the school. But fortunately, law and order is restored. So part of the protest movement was about many things, and probably a few percent, maybe 0.5% was about this machine on campus. It's a CDC 6400, a third-generation supercomputer that was used by students on the campus. And there was a professor. Oh, this is actually my picture from the time, the back panel. It was no machine for the poor. That was no wire wraps here, but twisted pairs, point-to-point communication, assuring an incredible speed and performance. And there was a young professor. Unfortunately, I couldn't find a picture from that time. Most of the pictures are original, but So this is a few years later, Butler Lampson, and Butler had this wonderful idea of teaching computer science using a language Snobol. And the only problem was that there was no Snobol system on the 6400. And Snobol is actually, if you look at it from in retrospect, it had a lot in common with the most modern languages. In particular, it was simple, but it was garbage collected, and it was type safe, and it was reflective. So it had all those capabilities. And for example, here's a program that counts the words, and you could do. Obviously, it was an excellent system for teaching computer science. So I was hired by the computer center, and pretty much illegally. I didn't have a work permit, but I wrote all the programs, and then they bought it from me at the end, which was actually a pretty good deal. But we calculate the number of hours I worked, and so don't tell it to the INS, Immigration Naturalization Service. It's called something different now. But so this is how the Snobol system looks today. It's beautifully bound. Probably the binding cost more than I got for it, but it worked really well. It was completely table-driven. You see the end of the tables. It's at around 200 octal, so that means it's about 1 kilobyte into the system. So into memory. The idea was that there was enough gap between the jobs on the CDC 6400. They came in big chunks, and there was always a little gap in memory, and we could run in that little gap, and we were running hundreds of student programs. So Snobol was actually quite a success. This is the complete team in a later reunion. It's a separate team, but the 3 people with the arrow are the Snobol people. Paul McJones helped me with the operating system, and Butler and myself. I found this on the internet, this picture, Butler. Have you seen this before? No. It's on the internet. I was searching for pictures of the 6400 and found this website. And guess what? It was about the Cal time shrink system anyway. So if you search for images of 6400, you find this picture. Great. So the success just a couple of anecdotes from that period of time. Butler and I watched the launch of Apollo 11, and actually the landing of Apollo 11 on the moon. Butler didn't have a TV, probably out of principle. I didn't have a TV because I didn't have any money, but I rented one. And since I rented one, you could rent TVs at the time. I rented a color TV for a week, and so we watched it together, and that was interesting. Butler also, once I made a mistake of bragging about how I may not be able to speak, but I can spell really well. And I challenged Butler to test my knowledge. And Butler said, "So how do you spell subtle?" And of course, he found exactly just a single word that I couldn't spell. But I can spell it now, believe me. So thanks to the success of Snobol, I was hired. I was still, I was a sophomore or whatever I was. I was hired at the Berkeley Computer Corporation, and here you see the BCC 500 in its glory, and it's hard to believe that the beautiful and talented Alto is the grandchild of this barely literate brute. It's the direct grandchild. Many mistakes were made in the development of this system. As I later said about something similar, they were all proprietary mistakes. That means that under penalty of law, you must never make them again. And one of the important concepts that I learned from Butler and Chuck, and I'm surprised that he didn't mention that word. It's bigorism. It's something that you want to avoid. So I also learned about memory hierarchy. So this is 1K of memory in RAM at the lowest level. Next, there is of course core memory. There's 8K, 8 kilobytes, all in bytes. So 8 kilobytes of core memory in the upper left corner, and the supporting electronics. And next comes of course the drum. about 3 megabytes of DRAM. As you see, it's about as big as a person. I was there one night. This is the actual installation. I was there one night when this drum burnt up, literally burnt up. It was rotating and it seized, and all the plating peeled off and jammed, and well, there was no fire, but there was the smell of amperes as we call it in Europe. And of course, at the highest level of the disk, it's about, I understand it's about 50 megabytes. This was to the right an upper that a machine is called a sniffer, and it's sniffing for avalanches of dust that will destroy the disk, and so it would stop it in time. Anyway, and this is myself from that time. We had wonderful accommodations, as you see. We had our own personal typewriter, teletype, and a cubicle too. So, and what are any anecdotes from this period? Let's see. Yes, I shared an office with Butler at Berkeley Computer, and how come that happened? Because I was so junior. The reason I shared the office because nobody else was willing. I thought it was an honor, of course. I quickly stepped into the breach. And the other thing is that one other memory is that Butler was writing this fantastic documentation. One night we were at the BCC 500, which was notoriously difficult to start. I mean, you had to push about, I'm not kidding, over 100 interactions with various buttons and switches and typing and so on to.
500 was an IBM Model 30.
That's right. That was right. But that was. I think that you could start it without the Model 30. But that's correct. That was really a big machine. But anyway, Butler one night just couldn't stand it anymore and put together a wonderful piece of documentation that from then on everybody followed to the letter. So notwithstanding the failure of the 500, I could follow the mod, as you call it, to Park. At that time I was working quarter time, still awaiting my imminent what's the word? They kick you out of the country because you're a foreigner. Deportation. That's what. Thank you. That's kind of repressed that particular word. So the other quarter, I was working for the ILIAC project. That was protecting me from the deportation because it was working for the government. So this is the beautiful grandchild, as we saw. But I want to focus on 1974 when Bravo was born. In the spring, I walked by Butler's office and casually looked at his desk. Typically, I didn't do that, but there were these either 2 or 3 pages of handwritten notes on his desk, and I was asking him what that was. And in fact, it was a design for an editor for the Alto, and in particular, these 3 items were expressed on those pages. Unfortunately, these pages were lost. They were lost pretty early on, so it's not like I lost them recently. I scanned everything I can, but from my memory, there was a screen update algorithm, and we're going to look at it in a minute because we don't have the original nodes, but we have the original code that was written from that node. So the screen update algorithm and how do you use the display list, which was a feature of the Alto to save memory because memory was still very expensive. There was a kind of a playing off the amount of screen space that you use with the amount of memory that you have for the program to run. So there was this algorithm there, and there was an implied document model which was a string of characters without carriage returns. There were carriage returns at the end of paragraphs, but not between lines. That was a very important concept of the document model, the first step to formatted documents. and for to WYSIWYG, the flowing of the characters, that there are no carriage returns at the end of lines, and also some tricks, the idea of a selection that is made by the mouse, and the typing buffer of how to type in. Now in the summer, or very soon, I implemented a prototype that was just showing a couple of lines on the screen, but we're using those algorithms, but it was clear that we would need more ideas, and so we extended in the summer to create this minimum viable product, as they would call it today, the MVP, that you needed a couple of more ideas. For example, how to store this string of characters and how to make the editing efficient, which wasn't in the original notes. And there's this fantastic idea by Jay Moore called piece tables that was borrowed. And piece tables mean that instead of operating on the string itself, you operate on a description of contiguous portions of that string. Called pieces.
Actually, I thought it up independently.
Oh.
I didn't know about Jay's work until a couple of years later.
Thanks for the correction. I thought it was it was right.
I think Jay actually thought of it first.
Well, I've heard it from you, of course, but then I somehow associated that you had it from Jay, but that's fine. I certainly got it from Butler. So that also means that the file pages could be cached in memory and at a random access. So we had a very nice arrangements whereby the editing time was proportional to the length of the session rather than the size of the document, which was pretty important at the time. We had a nice scrolling paradigm, which unfortunately got lost in the development of GUI as from the Macintosh. The way we were scrolling is that we pointed to a line that we wanted to go to the top of the screen, or pointed a line that we wanted to go to the bottom of the screen. It was kind of very natural. That's not how it's done today. Today, you go line by line. There was a third method, which Butler called thumbing, because you open the book with your thumb, and that's the analog, the random access into the document. And we decided on a modal user interface, not because we liked the idea, but because we wanted to get on with the MVP, and that gave room to other people, Larry Tesler in particular, to develop the modeless user interface that, of course, then that won the race. The story about the modal user interface was that if you were in the wrong mode and you type the word edit, that was EDIT. That was extending the selection to select everything in a document, and then delete it. Delete the whole document, and then insert the character T. So all your work disappeared, and T appeared on the screen. Yeah, it was undoable, but only to one level. So you could undo the insertion of the T, but you couldn't go back to the. Well, okay, there was another feature called replay, so it wasn't that bad. Anyway, so let me just. Well, we are running a little bit late, so let me just show you. This is Bravo of that time, and here's the update algorithm. Let me see if I can just follow this. You can see that it's November 74. There's a for each for new and old line, that kind of a compound for each. It's written in BCPL, and then really there are two parts. You either reuse the old line, or you format and display a new line, and then you do something MP line and the end. Now, this looks very trivial. The non-trivial part is the ifs that you perform in order to determine these conditions. What you do there, of course, it's obvious. But how do you do those conditions? That's critical, and how it's connected to the editing primitive. So it's deeper than it looks, but it's also very nice that you can look at a piece of code and actually see what it was doing. Now, this is also a key idea that Butler has been espousing, is the notion of the interfaces have to be very high bandwidth, or the wide interfaces. I don't know what the official term is. You know what I'm talking about? Right. But anyway, this high bandwidth and wide interface is that you don't call a subroutine to get one character. You call a subroutine to get a big chunk that is very easy to handle. And in this particular case, this was the mapping of the character in the document. Obviously, at those speeds that were factors of 2, 3, or 4 orders of magnitude down from what we are used today, it was very important that you did it this way. We were called to get the character, and what we returned was a long string that could be accessed very, very cheaply. And then at the end of that long string, we had to be called back. And what the routine did, it found the piece using a binary search, and then the piece was typically on a disk page. We found it in a virtual memory by a hash lookup, and then we have a little bit of trouble because we didn't have byte addressing at the time on the Nova, so we had to do a trickery, and then we are done. And there's some special code, special case for system text that is not on a file. So Butler, of course, wrote the wonderful documentation. Those were the days when documentation was valuable, readable, enjoyable. Today, it's the exact opposite. Educational, thank you. Today, it's exact opposite, and you know, why don't you help? Of course, this is the other page of the documentation again, very helpful, giving examples, giving notes, and so on and so forth. Here's a paper by Lois Lampson, and I want to stress this in the remaining 40 seconds that this was the first time, probably in history, that non-professionals, especially the spouses of researchers and friends of researchers, were coming in at night using computers. That never happened before. It was either a word processing professional who went that were using computers, maybe, and of course the computer scientists themselves, and they were creating work of this caliber, and documents of beautiful documents, and the acknowledgments to Mr. A. Bravo. A is of course for Alto, Mr. Alto Bravo, and at that point it was pretty clear that this opened up the world for applications. And I don't think it's an accident that today the second and the fourth largest corporations in the world in terms of the important metric of market capitalization are software companies. And I think that we are all let's see. So, I mean, in conclusion, I just want to thank for Butler's help and guidance and brilliant, far-reaching insights, and without which I don't think that any of us could have enjoyed the success that we had. And I think that everybody in this room would agree with me, and also some people who are not in the room. And I just want to quickly mention two of these people, referring to the fourth and second largest corporations. Bill Gates says if you could pick anyone to help you with complex system problems, you would pick Butler. At Xerox and Microsoft, he was a key person helping with the most complex problems. I only wish I had taken more advantage of his abilities. Bill Gates and Eric Schmidt, chairman of Google, says Butler is probably the broadest and smartest computer scientist today, and we all just tried to keep up with him and almost always fell behind, his word. His contributions made much of our world possible, and I am beyond grateful. Eric Schmidt. Thank you. So I have 3 minutes left for questions. Yes?
So Charles, the
key ideas in Bravo. Are any of those still in use today?
Totally.
I remember, well, let me tell you, I remember as a consultant once when the scientific workstations were coming out and people were building, they saw this kind of editor, they said, oh, I can do that too. Well, they couldn't. But I decided that the right answer as the consultant wasn't to try to teach them this stuff because it was beyond them, but rather to just wait for Moore's Law to save their bacon. And sure enough, a year later, their editor worked fine.
Well, that's true, but the competing editor will wipe them out because what happens is that you need this margin of safety. If you don't use it, somebody who uses that margin of safety will wipe you out because they can put in more stuff. And Moore's Law is great. On the other hand, the programmer's ability to use those cycles is much, much greater than Moore's Law. Oh, that's Moore's Law. Yeah.
Document hasn't increased.
Sorry, repeat it because
the number of pixels you're using on the display screen to show a page hasn't gone up much. The human isn't editing faster. So in fact, you have a lot of headroom that Moore's Law gives you to write simpler code.
Well, I think that's true, but I think you underestimate the complexity that either is in some of the programs or we are intending to put into those programs. And I mean, just to spell check to mention just one thing, that's the obvious thing, but there's so much more that I mean, there are software that I could show you that would blow your mind away and which requires the kind of margins that we are talking about here. But be that as it may, you had to oil you can't get there from here if there had not been a success in the beginning, there had not been an investment into Moore's Law. So it's not like you could have avoided that. Without this, nothing would have happened. Yes, Al?
Around, say, 1975 or 6.
Oh, we have my thesis has the exact number of lines, but I don't particularly recall, but it's the order of I would say 20, 30,000. Yeah. I mean, we are talking about, it's easier to say it, it's about 6 or 7 person years.
So the most interesting thing,
10 person years.
So I would take a contrary position to Bob and say,
right,
what's been interesting about Moore's Law in all dimensions is that the lines of code have gone up somewhat commensurately with Moore's Law, but not the utility.
That's certainly true now. But I mean, on the other hand, and I will agree. I will.
It was pretty good in 1975 and 76 as far as turning out a document, and I dare say 95% of all of the features that people use today were in that system.
No way.
No, well, okay. I think it was a great start, but let me agree with Bob for just a second and say that the fact is that modern languages, especially C# and to some extent Java, does give you a better platform and an easier way of solving problems at the cost of a modest and reasonable expenditure of cycles. But at the same time, you have to be cognizant of how to use those systems, and you have to use these tricks. And we are using these tricks. Yes.
So much of what you were doing seems to be working with a cleanish slate, and nowadays, a lot of software development is sort of handicapped by legacy. Yeah. So what's your thoughts?
Your screw legacy. I mean, it's. I think code. The best thing that you can do is delete code. I go every morning, and I ask people, how much code have you deleted? How much or replaced or deleted without changing functionality, of course. And that's a big goal. I think that the legacy sunk value is overrated. Sunk value is actually a negative value. If you want to get rid of it, you want to get the albatross off your neck, the greater the sunk value, the greater albatross it is.
If you take out a feature and General Motors has built its business on that feature,
it's the old damn version. It's not my problem. it's General Motors' stupid problem. It's why should I shouldn't prevent me from making money.
And Ballmer doesn't want to get those phone calls.
Yeah, I'm not working for Ballmer.
And neither are you.
Yes.
One thing I remember from working at Xerox is that Bravo was used, at least initially, to edit code as well as documents, and so all the compilers were written to ignore the little formatting sections that Bravo would put in the file. That's a legacy that did not survive, and I'm curious whether.
Well, I don't think it was that was had to do with the fact that the program editors weren't using GUI. Now, Visual Studio uses GUI, so it's quite fine. Also, formatting is now projected rather than inserted in the code. So actually, using formatting in code doesn't make any sense. It should be. It did at that point. But not even, the only reason it made sense is because the editor was convenient and the editor was doing formatting, but the editor was built in such a way that it was very easy to ignore formatting, fortunately. So yeah, that's a small period in time when that was important. Yeah, he's talking about small talk, of course. Okay, thank you very much. Thank you.